Hello everyone, Mr. Schultz here. Welcome to Integrated Math 1. We're going to be talking about exponential functions. This is going to be added into chapter 4, so make sure you're writing this down still, even though it says 8-1. Please write your information in the top corners. You will need some graph paper for this. So, identify an exponential behavior. So linear functions can be written in the following formats. We have standard form, where it's ax plus by is equal to c. Now we have slope-intercept form, which is y equals mx plus b. Now, hopefully you guys remember this. The part about linear functions is that they create on a graph a line. So if we're going to have an exponential, so I'll try it in, exponential function, it's a function of the form y is equal to a times b to the x power, where a does not equal 0 and b is going to be bigger than 0, but b does not equal 1. Now, we're going to get to this in a few minutes, why that is the case. All right, let's go on. So with a linear function, we're going to have something that has a constant rate of change. Now, you're going to see that, hey, look, it makes a line. So this is linear. This makes a line. It looks like a line. Now, this one right here, it looks like, hey, it goes up 2 over 2. So the delta y over delta x for this is going to equal 2 over 2. Now, if we look at the next one, it's going to be up 2, left 2. Okay, so it's still equal to 2 over 2. And then it does another 2 over 2. And then it does another 2 over 2. Now, the reason behind this is we have the understanding that the rate of change, stays constant. It has a constant rate of change. Now, we can see this when we put it into slope-intercept form, y equals mx plus b, that this m is our delta y over delta x, or our change, or our slope. It's the same every single time. Now, the problem with exponential that gets us is that it looks like a curve, and we're like, oh yeah, it looks like a curve, we're good with that. But what we're not good with is seeing the delta y over delta x. Now, the delta y over delta x for this one, we could see, all right, it goes up 2, so it goes from like 1, it goes from 1 to 2, that's 1, and it goes up 2, okay, so the slope is 2, 2 divided by 1 is 2, okay, cool. The next one, it goes over 1, okay, change is 1, delta x, the change in the x value is 1, and then it goes up to 8, that's 4, from 4 to 8 is 4. Okay, at this moment, we can understand that, hey, look, this is not changing at a constant rate. And we can tell that from a graph just by looking at it if it curves. If it curves, it will not have a constant rate of change. The only way it has a constant rate of change is when it looks like a line. So we're going to write this in and say, hey, does not have a constant rate of change. Get out of there. It changes. It changes. The rate of change changes. So it doesn't have a constant rate of change. All right, let's go on. So remember, you're going to check the rate of changes. If it's constant, then it's not exponential, but it's linear. Now, exponential function rates of change will look like, they look like a curve. Now, so let's write that in. It'll look like a curve. That's right, a curve. And so this could look like something like this, where it's going to go up, really, really fast. And we see this in like disease, like if we're going to study diseases or something like that, we see that, hey, it grows exponentially. Now, we could also have exponential decay. So if you have something like this, and it's going to come down really fast, and then it will come and it'll get really, really close to this x-axis, but it will never touch it. Kind of interesting. So we have both exponential growth and decay. Now, a really good topic to bring up is like radioactive decay, like Half-Life. Now, I know some people used to play this game called Half-Life way long ago, and it's, that name is from radioactive decay. Like, it takes this many years for half the the radiation, half of it to decay away. Like, after so many years, if it's 5-year half-life, then after 5 years, half of it is gone. And so that'd be exponential decay. Let's go on. So we can identify this exponential behavior by checking it out. Now, this is exactly like trying to solve for the rate of change. Now, we understand that it's going to be delta y over delta x. That's the slope. So what we can do and be like, all right, it's going to be plus 1, it's plus 1, it's plus 1, it's plus 1. So we can do a quick check and be like, plus 1. We're going to be like, hey, wait a second. This is not linear. Or, hey, it is linear. Now, I'm going to write it right here, but I'm going to do the real one to the right. If I go from 0.6 to 6, that's going to be plus 5.4. If I'm going to go from 6 to 60, that's going to be plus 54. Okay, wait a second here. So the first one is 5.4 over 1. And then it's going to go to 54 over 1. Yeah, that's not a linear. That's going to be maybe exponential. Well, let's see. Exponential is going to be multiplying. If you remember the arithmetic versus geometric was multiplying. So just plug in some information. All right, if I'm going to go from 0.6, I'm going to multiply what? Let's put d. 0.6 times d is equal to 60. Or no, 6. That's the next one. So let's erase that. All right, well, if you don't know it's going to be 10, you can simply divide this and be like, all right, divide by 0.6 on both sides in your calculator, and you get, hey, d equals 10. Then just do a quick check. 0.6 times 10 is 6. And then you're like, oh, wait, every single time it's times 10. And maybe we should go to the dot multiplication. And so each one of these, we see, hey, it's going to be times 10, times 10, times 10, times 10. Now, if it looks like times 10, not 11, if it looks like that, then it is an exponential growth. And it's going to be a multiplication, a geometric sequence. All right, let's go on. Now, that's exponential growth. It's growing. The other way is if it decides to decay. Okay, well, each one of these is plus 1, plus 1, plus 1. So I'm not going to write plus 1. I'll write it once. I'm like, all right, each one of these plus 1, plus 1, plus 1, plus 1. But we don't really need to talk about that too much. Now, we could say, okay, it's going to be minus 20, and then from here to here, it's minus like 16. Well, okay, so we know it's not going to be linear because the rate of change changes. But if we don't know what we can multiply to go from this number to this number, we can create an equation. 100 times, I'm going to put d is equal to 80. And now all I need to do is divide by 100 on both sides, and I will get d is equal to 0.8. And now when I put this into the calculator, and I times 0.8, and I times 0.8, and I times 0.8, I'm going to see, hey, look, it has an exponential decay of 0.8. All right, let's go on. When we're talking about exponential growth and decay, there's some key parts to this. So the key features of this function will be the following. If you remember your power rules, anything to the 0 power, so for example, 2 to the 0 power, that's equal to 1. 5 to the 0 power, that's equal to 1. 792 to the 0 power, that's equal to 1. Now, if you remember, when x is 0, that's going to be the y-intercept. Okay, well, what does that mean? Well, that's where it hits the wall. And that's where, hey, look, here's the wall, it's going to hit right here. If we plugged in 0 for x, these two will cancel out. So I'm going to cross them off right now. And we'd be left with our y-intercept would be 0.05. So that's our y-intercept. It's this a. Y is equal to a times b to the x power. A is our y-intercept. Okay, let's erase this so we can read a little bit more. Now, I also can tell that this b is going to make our graph grow because it's bigger than 1. If it was 1, we'd be like 1, okay, like 1 to the 3rd power. What's 1 times 1 times 1? 1. Okay, 1 to the 5th power. 1 times 1 times 1 times 1 times 1. Yeah, it's only going to be 1. So it doesn't do anything to our, it'd be a line just going left and right there. Horizontal line. But anything bigger than 1 will make it grow fast because it's exponential. So since the b right here, this 2, since b is bigger than, oh, no, the other way. Since b is bigger than 1, we have exponential growth. That's it. Now, I'm not going to go into the minutiae about it, but basically, you're going to have 2 to the whatever power. It's going to make it grow really fast. Now, if we're going to graph it, what we probably want to do is we'd probably want to just make our t-table. So let's go down and do that. So I like to put in some numbers. I like to put in some negatives. I like to put 0, I like to put 1, 2, and then I like to put like a bigger number, like 10 or something. Now, for this right here, this is pretty much going to be plug and chug. Like, so for the first example, we'd have y is equal to like 0.05 times 2 to the, and we could say, okay, negative 1 power. So if we do 2 to the negative 1 power, that's going to be 1/2. And 0.5 times that would give us 0.025. And then we would just plug in the number right here. It would be like 2 to the 0 power. And then we'd multiply it out and use the calculator, use our tools effectively. Like, we don't want to do this in our heads. And so yeah, we don't want to make as many mistakes as we want. So if we just use our calculator, I'm literally using my calculator right now. I put in my function and then I figured out, all right, I'm going to multiply this and this, and I just plugged in Chuck. So when we plug this into our graphing calculator, if we want to, or if we want to just plug these numbers into the graph, it would look like this: exponential growth. All right, there we go. All right, guys, let's try another one. So this is an example of exponential decay. Well, I'm probably going to have somebody be like, hey, Mr. Let's go back and talk about that. All right. So if you noticed, like when we plugged in 2, like 1, 2, 3, 4, 5, 0.5 right there, when we plugged in 2, there's a point right here. See this? And then at 1, it's 0, 1. And then at 10, I didn't put it, but like at these points, like you get a certain amount of points. And then you'd be like, after you get those points, then you'd be like, all right, it's going to look like this. And it's like you try to make it fit. Now when you're graphing a line, it's a lot harder than when you're graphing graphing a curve. It's a lot harder than graphing a line. All right, let's go on to the next one. So exponential decay. So remembering our function, we understand our exponential function. We now understand that it's y is equal to a times b to the x power. So we understand that this A right here is 160. That means it hits the wall at 0, 160. So I'm going to put this 0, 160 is the y-intercept. And because B is going to be in between 1 and 0, this is exponential growth. Oh, I'm sorry, not growth, decay. The other one was growth. This one is decay. It means it's going to get smaller, 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 smaller. So sometimes it's just easy to just think, all right, what's going to happen? Well, this is basically telling us, hey, every step you're going to times it by a half. So when I plugged in 0, half, when I plugged in 0, I should get 160. And then let's say it's like a half-life of 1 year. So after 1 year, it's going to be half of that. Well, half of 160 is 80. Now, if we plug this in the calculator and we did our inputs and outputs, this is exactly what would be happening. If we, year 2, it'd be like half again. Well, that'd be 40. In year 3, that would be 20. Now, hypothetically, if we went back a year, it'd be 320. But that's just hypothetical. Now, if we were to graph this, for example, in your homework you have to graph it, then we would just pick like 3 or 4 points and try to graph the curve. So here's the example. It hits at 160, which is kind of hard to tell. And then at 1, it hits at 80. And then at 2, it hits at 40, which is right there. And then 3, it hits at 20. I want to continue. So rather than a line where it's like you only need like 2 points and then you have your line, I'd want to have a little more points just to be on the safe side. All right, guys. Thank you very much. And I will catch you in class. You guys have a wonderful night.